Yeah. So that's a pretty short one. We're just going to talk about the use of the adiabatic relationships, because you can't do these types of reversible cycle problems without knowing about the adiabatic relationships. So let's talk about the two different kinds of reversible expansions and compressions. There's isothermal expansion and compression, which we've talked about, and we have the work equation that goes with that. But we're looking at the PV plot. And so if we have an isothermal expansion, this is just the ideal gas law, right? You could do P1 V1 equals N1 RT1, and you could divide both sides by the new conditions. P2 V2 equals N2 RT2. And I can do finals and initials, and that's what I have over here. But yeah, we would move that V2 over on the other side, so it'd be on top, the V1 to the other side on bottom, and the P2 over to the other side, it'd be on top. So that's what we have here. You see the P final is equal to P initial times these ratios. The N's cancel because we've got the same amount of gas. The R's cancel because it's a constant. And so we have this situation. Now look at this. Isotherm, the temperatures are the same, so the temperatures cancel. So the P final is just the P initial times the change in volume, VI over VF. Okay, now VF is larger than VI, so this is less than 1. Right, so that fraction is less than 1. So that means the PI is going to shrink and PF is going to be smaller, right? So this is PF, this is PI. So in expansion, naturally, the pressure drops. The volume gets bigger, the pressure goes down. This is simple. This is exactly what we would expect from the ideal gas law. Okay, the adiabatic expansion, that's when there's no heat. So how do we keep the pressure this high? As we're expanding, it would want to cool down, and so we're putting heat into it. So as much heat as we put in, that's how much work is being done on the isothermal expansion. So isothermal is delta U equals 0, which is equal to Q plus W. Therefore, I'm going to put it up here, therefore Q equals minus W. So whatever work is done by the system, that's how much heat we have to put in. We put in 10 joules of heat, 10 joules of work is done in the expansion. It's pushing that piston out. That's for the isothermal expansion. And when we say reversible, what we really mean is that it's at each point in there, it's at equilibrium. So it's at equilibrium the whole time. So the thermal equilibrium is maintained the whole time. If it's going really fast, guess what? That thermal equilibrium can't be maintained, and you start slipping down the adiabatic. So adiabatic expansion looks the same, but it's got a different slope. Let's explore why it has a different slope. So if we can't keep the heat going into the system and that expansion, we start losing that thermodynamic equilibrium, and we start going down a steeper path, which is called an adiabatic expansion, where the heat is 0. No heat is flowing in, and we drop pressure even further, and we also drop temperature. So in this case, the TF over TI don't cancel. The moles and the gas law, the gas constant still cancel, but TF and TI are not the same for the adiabatic. So here we have PF and TF. And here we have PI and TI. And over here, this PF, this is still TI, right? They're still the same temperature. We're on the isotherm. But on the adiabatic expansion, the temperature drops on the expansion. And so we could also look at this to see that because it's cooling, this is less than 1. And TF over TI, the final temperature is lower, so this is less than 1. So we have two fractions that are less than 1, so it's even further down. So pressure drops even further. So the initial pressure is times 2 fractions that are both less than 1, so it drops even further. So that's how we know it has a steeper slope, because the initial pressure is multiplied by 2 fractions that are both less than 1. Whereas on the isotherm, it's just multiplied by 1 fraction that's less than 1. And it's the same fraction because we have the same volumes. So therefore, the adiabatic pressure is always lower than the isothermal pressure for the same delta V. So that's the take-home lesson.
So that's TF to TF and then
This is and. These are ands. So PI and TI, and over here we have PF, and it's still TI because we're on the isotherm. But here it's PI and TI, and now it's PF and TF. So the temperature is changed too. So we have a different temperature. So that's my little and sign. That's kind of ugly. So my point is, it's not an isotherm; it's an adiabat. So we've had the temperature change as well. So let's look at some of these adiabatic relationships. And I just want to show that, you know, this piece, this nRTF and nRTI, that fraction, a lot of times we don't know all the variables that we need to know, especially in like a TF diagram or a TV diagram or a PV diagram. We're just looking at two of the variables. And so here, if we're looking at just the PV plot, we might have the P initial and we might have the V initial and the V final, but we don't know what the temperature did. And so this gamma up here is capturing this temperature effect. So that's why it's color coded. And this is new from your notes. I added this last night because I wanted to make it even more clear where that gamma comes from. We don't need the gamma if we have the temperatures and the volumes and the initial pressure. But a lot of times we only have two of the variables, not all three. So we're trying, you know, when we're trying to fill out the state variables table, we need all the pressures, all the temperatures, all the volumes, and all the numbers of moles. Sometimes we don't have enough variables. So this gamma is a property of the gas, and it will allow us to capture the temperature effect without knowing it. Or if we know the temperature, it'll help us capture the pressure effect. There's lots of different ways to write these relationships. This one is if you know the pressures and volumes. This one is if you know the temperatures and volumes. Okay. And this gamma, what is gamma? Well, this is gamma right here. It's the ratio of the heat capacity at constant pressure and the heat capacity at constant volume. Remember that Cp is equal to Cv plus R. So it's always bigger than Cv. So it's always greater than 1. Gamma is always greater than 1. Okay. So this is why. We typically know only two of the three variables. This is the three-dimensional plot. So notice we have the temperature here, the volume, and the pressure. Normally we're looking at a PV plot, but and so in these previous plots, this is a TV, but here's a PV plot. You see the isotherm and the adiabat. The temperature axis is going in and out of the page of the screen. And so we see that temperature axis down here. And so look what's happening. The isotherm is staying along a particular temperature, right? So this, you know, this is a particular temperature, and so that's the isotherm. And it's not going to stay. No, if you dropped a ball, let's say you set a ball up here. Let's do a little experiment. If I set a ball on here, it would not follow the isotherm. It would follow the adiabat, because the adiabat is straight down the hill. So the only reason you could follow the isotherm is if you're putting heat into the system. So that's kind of putting it's making the ball go down on the temperature axis, staying at the same value. And the only way to do that is to have a force that's kind of keeping it uphill a little bit. Well, that's heat flowing into the system. That makes it follow the isotherm. But if the heat stops, then it falls down the adiabat and it goes down that way. So let's look at how we get some of these adiabatic relationships. We did this integration in an earlier lecture, but it was for the for a slightly different reason. So this one is using the delta U, which is a function of the change in temperature. This is an adiabatic relationship, so heat is 0, and we're doing an expansion, okay? And we can start out with that minus P external times the change in volume, but we'll make it a small change in volume. We'll kind of integrate our way down. And so let's integrate the left with respect to temperature, okay? And we'll integrate the right with respect to volume. Now, in terms of this pressure can be substituted with nRT over V. So we had nRT over V. Where'd the T go? Well, the temperature variables are over on the left side of that equation. And so we moved the T over here. So the pressure went down to nRT over V. So we got the V, we got the nR, and the T went over on the other side into the denominator. So that's where the temperature came from the pressure term. And now it's very simple. We can integrate both sides. This is a very simple integral. Integral of dx over x is the natural log of x. And we evaluate that at both limits. And so the natural log of the initial temperature minus the natural log of the final temperature would be the ratio of those. And the same here, the natural log of the initial volume or the final volume would be the ratio of those. So here we have our integration is finished. And then we can move some things around. And so this R right here, we're gonna do everything in terms of moles, and so and we have a number of moles on both sides, so we can cancel those. And remember that CV or CP is equal to CV plus R. So R is equal to CP minus CV. So that's what's happened here. This R comes down, and we have CP minus CV. Now I can move this CV over here onto this side, and I can kind of split that denominator. So I have CP over CV minus CV over CV, and so that's equal to 1. And this is gamma. So this piece is gamma, this piece is 1. And I can take this, since it's in front of the log, I can move it over here to an exponent. And I can get rid of the logs on both sides. And so this is our relationship of volume to temperature. And so if I know the initial temperature, if I know the initial volume, the final volume, I can solve for the final temperature. And I don't need to know the pressures involved. So this is the whole point. If I know temperatures and volumes, I can get that fourth one, that final temperature. And I don't need to know the pressures. So this is what helps me fill out the state variables table. Now we can use the ideal gas law to come up with the other relationships. And so like if we solve for temperature here, PV equals nRT, so T is equal to PV over nR. And so we could then put those in here as ratios and cancel the things that don't change. And we could come up with other relationships where I had volume and pressure instead of volume and temperature. And so that's what we're doing here. So we have the temperature volume one. If I wanted to swap that around and put the exponents on the other side, I just invert the exponent. So that's the temperature ratio, and it's 1 over gamma minus 1, and then I've got the volumes here. This is the one that we'll use most in the tables, because a lot of times we have the hot and cold temperatures in an engine, and we have one of the volumes and we need to solve for the other one. So this one is a very useful one. This one here, yeah. And now, like I said, if I wanted to get rid of the temperature and put in pressure, then I could use the ideal gas substitution, and the NRs would cancel, so these guys cancel. And so I have this PI over PF, this piece here, and I have the VI over VF. And here I've got volumes on the left and volumes on the right. I don't like that algebraically, so I'm going to move those volumes over to the other side. And so if I move that over, then this VF goes over here, so that's VF, and this VI goes down here, that's VI. And so it's this gamma minus 1, and then I have another one of those fractions multiplied by it, which would be plus 1. And so gamma minus 1 and plus 1 just gives me gamma. So this is a relationship. If I know the pressures and the volumes, but not the temperatures, then I could solve for the final pressure. So these are our let's see, I guess we've got V and T, we've got V and P. The third one that we could have would be a temperature and a pressure one. So I don't know if I have that one solved. Let's see. Yeah, it looks like I've got volume and temperature and pressure and volume. Okay. So what is this gamma? Well, gamma is required for these adiabatic relationships. And so an isotherm has a gamma of 1. Okay. But what is gamma for helium? Remember that helium can only translate. So all of that effort that you went through to learn about the degrees of freedom for, an atom or a linear molecule or a bent molecule comes into play here when we start getting into engines. So what is pushing the piston? The adiabatic relationships and the isotherms, the type of gas is gonna matter into how much work you can get out of it. So look here, we've got CV, and I want to make sure that you guys understand where all of these numbers come from. So CV is 3/2 R. Why is it 3/2 R? It's a review question. And I tested you on it, so you had to study it. And there's a hint on the screen.
The translation rotation.
Yeah, but there's no rotation. So it's just translations. It's just translation in X, Y, and Z. Those are the 3 of the 3/2. So you get a half for every direction. So X, Y, and Z, translation only, 3/2 R. Now, where the 5/2 R come from the CP? Remember that CP is equal to CV plus R. So since we're dealing in halves, I'm going to add 2/2. That's the same as adding an R. So I go from 3/2 to 5/2. So that's CP over CV. So this is CP, this is CV. And I can cancel some things here. I can cancel the R's, and I can cancel the halves, and I end up with 5/3, or 1.67. That's equal to gamma for helium, or for neon, or for argon. Any atomic, single monatomic gas is going to be have a gamma of 5/3. Now let's, just for grins, let's do this gamma minus 1. Gamma minus 1 for helium. Again, if this is gamma, then what is 1 in terms of thirds? 3/3, right? So 5/3 minus 1 would be 5/3 minus 3/3, or this would be 2/3. Okay, for helium, for He. Okay, what about 1 over gamma minus 1? Well, if this is gamma minus 1, 1 over that is just 3/2. You just flip it over. So this equals 3/2 for that exponent for helium. And if we're doing the pressure-volume relationship, gamma is just 5/3, right? We just determined that over here for helium. So those are all the numbers for helium that we would use for these relationships. But you got to make sure you use the right one. It's not just gamma. If you got temperatures and volumes, it's gamma minus 1. And if you know the temperatures and you're solving for the volumes, it's 1 over gamma minus 1. And if you have the pressure-volume relationships, it's just gamma. So guess what? Those go on your note card, right? And you got to make sure you use the right one. And I guarantee I'm going to be testing you on using the adiabatic relationships, because that's the one thing that people cannot do in the Carnot cycle. And it's a long enough problem that I'm probably going to ask you to do the whole darn thing, but you will be asked to do an adiabatic relationship. What's the final pressure for this adiabatic expansion or that kind of thing. Okay. All right, for CO2, now we can have rotation and translation. So trans and rot. Okay, but it's a linear molecule, so we have 5 halves, or we only have 2 rotations. So 3 translations and 2 rotations. Because in a linear molecule, the rotation around the z-axis is not defined. There's no atom off the axis. So you only have rotation around x or rotation around y. So that's your 5 halves R. And then the CP is another 2 halves. So the 7 halves R is CP. So these things cancel. The R's and the halves cancel. So we have 7/5 as our gamma, or 1.4. And then 7/5 minus 1 would be 2/5, and so that would be up here would be 2/5 instead of 2/3, and 1 over that would be 5 halves. And so this is, all of these are different depending on the type of gas that you have. So CO2, so you kind of see the steepness. An isotherm is got a gamma of 1. Helium has the largest gamma, so it is the biggest drop. CO2 is 1.4. Let's do water. So water, now we have 3 translations and 3 rotations. So we have 6 halves R for CV, and you add another 2 for CP, so that's 8 halves R for CP. We can cancel the 2's and the R's, and we can divide everything by 2, so we have 4/3 for gamma. Gamma minus 1 would be 1/3. 1 over gamma minus 1 would be 3, and just plain old gamma is 4/3. So this would be 1.33, and you can see water doesn't have as steep an adiabat as CO2, and that doesn't have as steep an adiabat as helium. This isn't just efficiency for getting work out of a system, this is also efficiency for refrigeration. And so monatomic gases would be better for refrigeration as well. You'll get a bigger temperature drop between your hot and cold reservoir with a monatomic gas than you would with water, say. Any questions on this? This is a really important page, because if you can't get gamma, guess what? You can't do the calculation right. But hopefully I tied it to things that you can always remember, the translations, the rotations, and the vibrations for the molecules. And we don't calculate any of the vibrations because they're not hot enough to activate those vibrations typically.
So gamma is always 1.
I would say gamma's never 1. Yeah. Well, the isotherm is a special case, but I just was showing you why the slope, the isotherm has the most gradual slope. So it's not really an adiabat. So the adiabats, these bottom 3 are adiabatic relationships. So these lines are adiabats, and this top one is an isotherm. And I was just showing how the isotherm, if you were to treat it the same way as an adiabat, would have a gamma of 1. But the true adiabats all have gammas that are greater than 1. Yeah. Okay. Now that's a good thing to clarify. Okay. So let's see how this helps us. So here's our state variables table. And we are typically, in automobiles specifically, but also most engines, you're given the displacement of the cylinders and the compression ratio. Even if you can't, even if it's not stated on the engine, you may just have the displacement. You can put a pressure monitor in the cylinder. You can take the spark plug out and stick a compression meter in it, and it's just a pressure gauge. And you turn the crank one time, and that piston pushes that gauge, so it's back, and you have the room, 1 atmosphere pressure. You put the thing in, seal it against the hole where the spark plug goes, and turn the engine over, and the gauge goes up as the piston compresses, And the gauge has a little needle that it moves, and it leaves it as a max. So you can see from 1 atmosphere to whatever, then you've got the compression ratio. So we're always going to have the compression ratio, and we're always going to have the displacement in almost any engine that we come across. And so we can relate those to the volumes in this cycle system. So the cycle goes from A, B, C, and D. Those are the 4 state variable points, and we have the 4 legs or segments, 1, 2, 3, and 4, which are the transitions. These are isotherms here, there, and there. And the adiabats join those. So the adiabats are here connecting B and C, and here connecting A and D. A lot of times in the problems, you have to be given the temperatures. And so you're given the hot temperature and the cold temperature. So before we get into all the complicated calculations, look how the table is constructed. Notice A and B have the same temperature. That's what isotherm means. And that's the highest pressure, so that's got to be the highest temperature, right? If it's something's hotter, it's going to be higher pressure. If something's colder, it's going to be at a lower pressure. So you've got to really get that in your head, that A and B are the same temperature. A lot of times the students will screw that up, and they'll have, like, the middle 2 will be T hot, and the top and bottom will be T cold, and your table is totally messed up at that point. Or they'll do something crazy like hot, cold, because they don't know, right? And they'll just put in the wrong numbers in the wrong spots. And so A and B are an isotherm, and so they have the same temperature. And then C and D are on an isotherm. Okay. And then from the displacement, we get, in the compression ratio, we have 2 numbers, we have 2 equations and 2 unknowns. And so we're able to solve for that. I've got the algebra on a different page. And so here we have VA, which is given here. Down here at the bottom, this would be VA and VC. And we know those. These are the 2 that we don't know. We don't get those from the displacement or the compression ratio. Does it make sense that VC is the largest volume and VA is the smallest? So the piston, when it's all the way up, is at VA. And when the piston's all the way down, it's at VC. So you get the largest volume and the smallest volume. Those are easy. Where, when the piston's going out, so this gas is pushing the piston down, where does it change from an isotherm to an adiabat? That's VB, and that's not easy to know, is it? Right? There's no point in an engine mechanically where that changes from the isotherm to the adiabat. Somewhere along that spot at VB, as it's pushing that piston down, it will change from an isotherm to an adiabat. So we need to find that VB, and this is how we do it. We use that adiabatic relationship. So we have the 1 over gamma minus 1, because we're dealing with the temperatures. We know T hot, T cold. Okay, so TC here is T cold. That goes right there. T hot goes right there. And VC, notice VC is the one that we use because it's connected to VB with the adiabat. So this equation is the equation for that line right there. It's the adiabatic relationship. So we're using C to give us B because C and B are on the adiabat. Does that make sense? That has to make sense to you. Because otherwise, you've got this equation. Do you put VA in here or do you put VC in here? VA is over here, and it's connected to VB with an isotherm. So we're not going to use VA. We're going to use VC because this is an adiabatic relationship. It describes the adiabatic connection between C and B. So we put VC right there, and then we have all of our variables. We know gamma, we know the temperature cold, we know the temperature hot, we know the volume C. And we're able to calculate VB. Once we know that, then we can calculate all of those other pressures. And then down here, how do we get V, the volume at point D? Okay, that's connected by an adiabat with volume A. So volume A goes here. The temperature A goes in that slot. The temperature D goes here. And we know gamma. And so we have all of our variables. At that point, you just plug it in and go. And you can calculate the volume at point D. And then once we have that, we use the ideal gas law to calculate all our pressures. So that's how you fill out the state variables table for the Carnot cycle. And next time we'll do the Carnot cycle calculations. Okay. How do you get some of these numbers? Well, there's lots of things online. Like, let's say I wanted to get a little more performance out of my Dodge Charger or my pickup truck or whatever. I could go in and I could change the displacement on my cylinders by boring out the cylinders and getting a little bit larger piston. And so I would just have more power because I'm pushing on a wider piston. I can get more torque and more power out of it. So they have these calculators that you can go in and you can type the length of the stroke. You have to know a lot about your engine, how thick the head gasket is, the combustion chamber volume. You hear the Dodge engines are always talking about a Hemi. What is a Hemi? Well, this top here, this head is a hemisphere. So that's what they mean by Hemi. It's a hemispherical head. You've heard that a lot, yeah. Some of them are flat. They just have a real flat top to them. So you could have a flat top, or you could have a hemispherical head. So a hemispherical head, that's what Hemi means. Okay, and so you've got that dome volume that you're calculating and everything, and then you've got the compression ratio, and you can calculate the statistics on your engine. So here we get the displacement and the compression ratio. Let's do the algebra here, and we'll finish with this. So delta V, that displacement value. So like my truck is a big engine. It's a 5.7 liter. So 5.7 liters, that's the difference between VC and VA. But I don't know what VC and VA are. I just know the difference between them. So that's one equation. The other equation is the compression ratio. That's the ratio of VC to VA. I got a big volume and it's squeezing down into a little volume. That's the compression ratio, VC over VA. And so I can rearrange that and solve for VC using that top equation. And then I can put these pieces right in here. And then I'll have all VAs in my delta V equation. Okay. And so then I can simplify this. And so that is pulling VA out. I have delta V as VA over times RC minus 1. And then I can divide both sides by RC minus 1. So this is nice. Now I have my A volume as a function of two numbers that I can read off my owner's manual or measure with the little compression gauge. And then I can put that VA piece up here into this equation. So this piece can go up here. And I can solve for VC. So VC is delta V plus delta V over RC minus 1. And so that way I can get those numbers. And you can find these. This is from the, I forget. I think this is, Nissan and Toyota. You can find the specs on all these engines. You've got the displacements here. You've got the chamber volumes and all of that. So you could get the compression ratio. Oh, you've got the compression ratios here. And so from all of these, we could get our A volumes and our C volumes, and we would have to do some guesses as to what the temperatures are. But the temperatures are what really change when you push on the gas. When you push on the gas, the cylinder heats up, pushes harder, you accelerate. When you let off the gas, temperature drops, engine's less efficient, you slow down. And so really you're controlling everything with the amount of temperature, and that changes the pressures and changes how it pushes on the cylinder. So we'll start here next time, and we'll actually do the Carnot cycle calculations.